Okay, so problem 4 is another Star Wars problem. This is Luke being shot down, Battle of Hoth, and he basically runs under this Imperial Walker, which is a big, mechanized war machine. And to start with, let me see if I can get the right. There we go. To start with, he uses a magnetic gun, a little magnetic cable gun, to shoot a cable up to the belly of the Walker and lift himself up. So there's a little motor on the cable. Attach his belt somehow, and so he goes doot, 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 doot. Okay, so the first thing he's going to do is he's going to go from the ground, which I'm going to call 1, and I'm going to do it with a different color, maybe a darker green. So I'm going to call it 1, and there's 1, and then he's going to go up to 2, which is right underneath the belly of the Walker. Let me see if I can just make this pen slightly thicker. Okay, ink opacity, let's go all the way up. Okay, so there we go, and he goes up to the belly of the Walker, and the height difference there is 15 meters, which I'm going to call H. Okay, so let's start with that one, and what average power does the motor have to produce to lift him to the other side of the Walker in 5 seconds? So first we have to find power, as you'll recall, is work divided by time, right? So first we have to find the work done by the motor to get him up there. So pretty simply, if you want to, you can say change in kinetic energy for Luke is going to be the net work done on him. And what's acting on him? Well, there's the tension in the cable, which is lifting it up, and that's provided by the motor. So that's really the work, the work done by the motor to lift him. And, of course, the work done by gravity, which is always acting on him. And then you get, this is equal to the work done by the motor minus Luke's change in gravitational potential energy. And so what you get then is the change in potential energy for Luke plus the change in gravitational potential is how much work the motor has to do. So that's not terribly hard then once you get there, because the change in kinetic energy, if he starts and stops at rest, is 0. Okay. The change in gravitational potential is his weight times the height change he goes through, which is h. He goes up h. Okay, so the motor does work mgh. And then all you have to do then is plug in work done by the motor divided by the time, and you get the power. Let's see. The power output of the motor. So power output of the motor is work done by the motor over the time, and that's given, right? 5 seconds. So then you get to mgh over T. And I meant to say, of course, that Hoth has a gravity field equal to exactly 10.0000000. I'm giving you like 6 decimal places. I happen to know that the gravity on Hoth is exactly that. So just make it easy and use that instead of 9.8, please. All right. So what that gets you to is then Luke's mass is 75 kilograms, and G is 10 meters per second squared, and h is 15 meters, and that is all divided by 5 seconds. So let's see, 3 times 75 is 225. So the power output of the motor is 2,250 watts, which is enough to light, 2,200 watt bulb. So it's advanced, Star Wars universe, power supply that fits into Luke's belt buckle or whatever it is. I mean, if you see the movie, basically just the belt lifts him up. Okay, so anyway, that's where we get to. For B, after he gets released from the underside of the Walker, what's Luke's speed when he hits the snowy ground? So let me see if I can find the eraser there. Oh, this is a smaller eraser. Smaller and hard-edged. I got to remember that next time. All right, so anyway, after Link. Yeah, it's Zelda, right. Okay, sorry, after Luke releases himself from the underside of the Walker. So, if you've seen the movie, once he's up here, he uses his lightsaber to cut a hole in the Walker and then throws a grenade inside and then detaches the cable and falls to the snow. So he falls that whole distance back down. So he starts, up at 2, and then he goes whee all the way down and hits the ground, which I'm going to call 3. Okay, so we can either do you can do a delta K equals net work. In this case, the work done on him, there's no more motor, right? It's the same as step 1, except, no motor. So it's just work done by gravity, which is, of course, negative delta U g. So what you can say is change in kinetic plus change in potential equals 0, which means you can just find his, well, I mean, it's pretty easy, right? So initial kinetic energy is 2, and his change in potential energy, however you want to measure it. You can measure this as being u equals 0 or this as being u equals 0. It doesn't matter. But he drops a height h, and his weight is, of course, still mg, so there you go. And what you'll get then is K2, or sorry, wait a minute. Yeah, that's K2, right. K2, let's see, actually not K2, sorry. K3 minus K2 equals, oh, right. So minus mgh equals 0. There we go. And since K2 equals 0, you just get K3, which I'm going to go ahead and plug in 1/2 mv3 squared. So K3 is his kinetic energy against the ground, and this is just the standard kinetic energy formula. So there we go, 1/2 mv squared minus 0 equals mgh. So what you're going to get out is v3 squared equals 2gh when you cancel the m and move the 2 over. So I think, let's see, g is 10 here. Height is 15 meters, so that's 150 times 2 is 300. So v3 squared is going to be 300, and then the units are meters per second squared times meters, so meters squared per second squared. So whatever the square root of 30 is, let's see, it's more than 1/6. Me cannot do math. I was like 17, I think, isn't it? Yeah, so it's like V3 is around 17 meters per second, whatever. You can figure out, you can plug 300 in your square root and hit the square root button. I'm not going to do that for you.